Ming Zhang is a distinguished architect at Synopsys. He leads the corporate strategy for 3D IC. Prior to Synopsys, he has been a circuit designer at Intel, uh, specializing in low power and fault tolerant designs. He was a foundry engineer at Samsung who specialized in DFX, software developer at AI startups working on algorithm development and cloud deployment. And most recently, he is the co founder and CEO of a chiplet startup, Zglue. Uh, Dr. Zhang holds a PhD in VLSI from UIUC, an MS in MEMS from UIUC, and a BS in physics from Peking University in China. He's going to talk to us about road to chiplets and the next 1000X. With that, Ming, welcome.
Thank you, Ravi. Thank you for my fellow speakers and everybody who came here to listen. So good morning, good afternoon, good evening. I just really like to borrow a line from Jan, right? I love it, right? Except that my time in industry is 4 times shorter. So in the past 7 years of me doing chiplets, I must say this is the most exciting pivotal moment of chiplets. I'm seeing a future into the next 1000. I'm so glad to be here to share some of the opinions I have. Let's travel on this road. So today, I'd like to talk to you about why we believe chiplets are becoming the road into the future and where are they typically used. And comparing chiplets or 3D IC or 2.5D IC to conventional monolithic chips, what exactly are now different in terms of architecture, design, and manufacturing? And how can we together, the industry, right, the semiconductor industry, manufacturing, EDA, chip OEMs, how can we work together to give wings to the innovators of the next 1000X? So these are the things that I want to discuss today. Why chiplets? System of chiplets are being integrated to put together to achieve the best class functionality. So in other words, the best PPA per volume. And larger SoCs are being broken into pieces, primarily due to yield and cost reasons. And if we do things correctly, regardless whether it's integration or disaggregation, we can actually accomplish faster time to market and better security. All right. So looking forward to a future of better PPA, lower cost, faster time to market, time to innovation, and a higher degree of security. Where are chiplets designs typically used? It's being used for typically for integration, heterogeneous integration, such as optical systems, as Sandeep mentioned, and network switches or networking SoCs. And disaggregation is usually driven by the bigger chips, such as data center or AI. But regardless, this is really being driven by the demand for better performance, lower cost, faster time to market, and a better secure product and a supply chain. We have been fortunate that in the past 7 or 8 years, the bigger chips are driving the growth, right? That's really the data center networking chips, right? There's some data here that it's being said that the total SAM is about 6 billion in about 2 to 3 years at a CAGR of 10%. And we're looking at possibly 10 times of that in another 12 years. Beyond the initial driver of HPC, the bigger chips, we're seeing a lot of potential for mobility chips, wireless chips, or other consumer automotive IoTs, right? At this point, the market share is fairly small, right, compared to the 6 or 60 billion. But if we believe in the future of smart everything, connected everything, all of these will become embedded with heterogeneously integrated or disaggregated chips. So hence the really big market in 2035. One of the interesting things about semiconductor is the application always drives technology and IP or tooling, right? Here's a diagram that shows the application distribution. You can clearly see that again at this point the primary applications are driven by the bigger chips, such as the servers, the AIs, and a little bit of telecom, right? Not a whole lot, but certainly it's a very balanced distribution here. In terms of technology node, we're seeing a lot of application of 7 nanometer. We're seeing a little bit more on both ends. On the higher end of 3, there's definitely some activity. And there's a lot of usage still for 12 and 7. How do we design a system that can accommodate various combination of process nodes on various advanced packaging architecture? That requires basically a menu of interface IPs, whether it's higher speed serial or lower speed parallel. So application really drives the menus of options for manufacturing technology and IP. So we're seeing this trend of evolution of advanced packaging in the past decade or so. I'm kind of trivializing this a little bit, but it's just to show a simple trend, right? It's really going from two-dimensional, simpler package to 2.5D, whether it's organic or silicon, and into the true 3D, right? True 3D, such as hybrid bonding or a mix and match of 2.5D and a 3D. Generally speaking, the complexity of the system increase, the density increase in terms of the bit per second. Due to the design constraints, it actually drops. But that's the whole point. That's the system level design optimization. You can potentially make bigger and higher density packages as you go from the left to the right. So one of the greatest challenges and opportunities, in my opinion, for chiplet-based design is that we just have way too many options, right? Option is a good thing, but sometimes permutations of technology is confusing. But we just have to get clarity out of confusion. So this is a picture that shows sort of the landscape of packaging leaders, right? Going from, again, the 2.5D players to the bridge to the 3D space. And as you can see here, it's really a trade-off, the manufacturing point of view, the density of bump or pitch or routing versus the density of the complete package, right? You're observing on the order of 100-ish, 1,000-ish differences here, right? But nothing in life is free. It's all about the designers are being offered a really good deck of cards, right? Every single one of these suppliers, partners producing a particular technology is a really good card. How do you play a best game? How do you permutate the different cards to play a best game, right? Different combinations of technology, different combinations of interconnects, different interface IPs, and how do you put them together quickly, robustly, and cheaply, hopefully, right? It's all about that. How do we play a game? We're being given a really good cards. Again, let me just say that I'm really excited listening to Jen and Sandeep's talk earlier because it got me excited. Right? This is probably the most pivotal and exciting moment of chiplet, at least as far as I can see, for the past 7 years. I've been doing chiplets for the past 7 years. Now, how do I look forward? I really think we as the industry really should focus on answering this question. How do we as an industry give chip designers the ability to innovate better, faster, and cheaper? How do we help them? It's not us. It's not about us. It's all about the chip designers, whether it's company, whether it's academia, whether it's research institutions. In my opinion, I think we need to do 3 things. Number 1, we need to recognize the new design targets. What has changed in terms of architecture? Number 2, let's give them wings so they can fly faster and make better products at a higher quality. Let's show them the road. Let me talk about every one of the 3. Well, there's no surprise. Traditionally, the design target for SoC has always been PPA, pretty much, right? Ever since I started in this domain, that's always like that. So what has changed? Well, in my opinion, that I think the first thing that has changed or will be changing is that we're going to be looking at more variations or diversity of designs, right? Rather than looking at a handful of product SKUs, maybe we're looking at 10x of that or 1,000x of that. Because really, in order to deploy chips into a world that's full of personalized electronics, whether it's high end or low end. We really need to have personalized and customized chips. Now, what does that mean, right? For customers or innovators, you really want to enable them to explore the menu of functional blocks and manufacturing options early. So before you go and commit to a $100 million chip project, how about you play in the sandbox first? What are the IP blocks? What are the interface connections? And what are the manufacturing options? All this really nice deck of cards I showed earlier with the 2.5D and 3D, right? So the answer to that is to have a library of verified interoperable blocks and some manufacturing models and maybe some standards, right? Standardization is hard, but it must be done. The second thing is velocity of innovation. I think we want to have napkin to product faster, right? Napkin to first product faster, napkin to revision product faster, everything faster. So you really like to have a design environment that's truly end to end. So you can go from A to Z within the same cockpit as opposed to jumping between tools. Do it faster, fail faster, succeed faster, end to end. Finally, well, if you're going to deploy billions of chips or maybe trillions of chips, you better make sure these chips now that it's spread it out in your car, in critical factory, maybe in your coffee cup, right? You want to make sure they can tolerate temperature, vibration, and all kinds of partial failures, right? So shipping a thing that has a fixated guard band and hopefully it'll work for X number of years, that used to work. It's not going to work anymore with this many chips. And why is it relevant to 3D IC or chiplets? Because now the systems, 3D IC is a big chip. The bigger the chip is, the more complex it is, the more likely something will go wrong. So we really need to have a way of SLM, silicon lifecycle management, to continue to detect and monitor the chips, even if it's deployed in the field and taped out at the guard band. That's the design target. In a perfect world, this is what I believe the world needs, right? This is the perfect journey for chiplet-based design. Exploration, design, and manufacturing. You want to explore as much as possible with your choices and know how much you're paying in terms of actual cost and PPA. Play a little bit before you design. And when you do design, you want to design rapidly from napkin to Nellis to GDS. And there's going to be a lot more variations. And you want to optimize really hard because, again, for 3D IC/chiplets, there's going to be a lot more corners. There's going to be a lot more uncontrollable parameters simply due to the supply chain complexity. And if everything is said and done, you played a little bit in the sandbox, you actually design the chip. Let's manufacture robustly. We still want to make money, right? So low cost, time to volume, and making sure everything works safely, securely, reliably in the field remains important. This is an ideal journey for chiplet-based design. A total solution has to be and must be a summation of three things. It has to be a total solution is one, interface IPs that connects the Lego blocks with or without a standardization, preferably with standardization, of course, and a design platform that's truly A to Z that supports integration and disaggregation flow with analysis and interface to manufacturing enablement, right? You got to do it. And also a monitoring mechanism so that the chips live longer. All right, so I talked about the new design targets. How do we give the designers of the chips wings? How do we give them wings? How do we make them go faster? Well, once again, let me recap. Diversity of the design is important. We need interoperable blocks. We want to make them innovate faster. We want to make their products live longer, right? This is what we want. So the first thing we can do is to give them a really good menu of IPs, regardless what cards you're dealt with, regardless whether you have 2D, 2.5D, 2.5D, and 3D, or 3.5D. Maybe one day we'll have 3.5D, right? We really wanted to offer the designers a really good menu to choose from, whether it's parallel, serial. At the end of the day, it's all about a trade-off of millimeters, micrometers, gigabit per second, picojoules, nanosecond, and your choice of cost and architecture, right? So having all kinds of IPs that support the connection of interconnects in Lego blocks are really important because we want to enable the manufacturing of various use cases on various manufacturing options. One of the biggest challenges for chiplet-based design, in my view, is that it could be both intuitive and convoluted, right? The fact that it can be intuitive is it's actually really a big chip, right? One way to really trivialize it is to say it's nothing but a big chip, right? It's a big chip, but I think the challenge is that just intrinsically speaking, the complexity has exponentially increased, right? The number of wires, the number of materials involved, and the number of suppliers involved, and also this length of design cycle is much longer. So hence the point that to really give wings to the designers, a unified design platform that goes from A to Z would be really helpful, right? It would increase the throughput of the design. It would also make sure you can discover early success, and more importantly, bugs and failures early. Here's one example of how it could work, right? We could have a single design platform that goes all the way from playing, pathfinding, architecture, deep into the weeds of PNR and custom circuits, and then toward the tail end, extraction, circuit simulations, and CP, signal integrity, power integrity, thermal simulations, and finally, as you're closing to the back end, you're trying to sign off for corners. You want to have some kind of a hierarchical concept so that you can sign off without having to deal with 100+ corners, but rather instead fewer, but still have hopefully the better quality. And more importantly, that I think Sandeep also mentioned the test, right? We want to make sure that all the DFX, in particular DFT and DFD hooks, are being plugged in to the 3D IC system as a proactive thought, as opposed to an afterthought, right? So having a unified design platform that goes from all the way from A to Z is really important. A being architecture definition, early planning, early modeling, and Z being finished product that lives forever. Now, the third piece, long live the chips, right? 3D IC chips are really a bigger chip, right? Whatever challenges that we had faced in terms of guard bending, reliability monitoring, or variation monitoring, or DVFS, that kind of thing, fundamentally, it's still there. The only thing I'm highlighting is that because of the complexity, two things have changed. One is the complexity. 3D IC is a much more complex system compared to a monolithic chip, right? That's one thing. That's just intrinsic. That's physics. The second one is just the supply chain, right? There's just going to be simply more suppliers, right? There's going to be more things coming from different people being cobbled together at a single destination at the assembly. We need to carefully think of a way to deal with variations, right? Guard banding stacking would be possible, but it will be challenging. So the one possible way is to better leverage the undie or unchip sensors, right? It's still the same thing. We use the PVT sensors, we use some other proprietary sensors to monitor environmental fluctuations that are macro scale, or we monitor per chip specific variations that could be a single chip thing, or it could be a fatigue driven by an aging thing, or whatever it is. We're going to react to it. We're going to move the systems from one operating point to another when it's allowed, right? So that's really the way we would make sure the chips live longer, especially for a complex system of 3D IC. So to kind of recap a little bit, that I think some of the things that I'm seeing here for the future of chiplets are, we are potentially going to be complementing the original design target of PPA with three more things. More product SKUs, right? More chip SKUs, a demand for higher velocity of innovation, whether it's truly driven by velocity or chip shortage, either way, a faster time to volume, faster time to innovation would help. And finally, given the complexity, we want the chips to live longer. We as an industry have the answer, right? It's having interoperability, standardization, end-to-end design flow, and having a mechanism to extract data and react to it in field. There's a repeat. It's a total solution, really a total solution of chiplet-based design really should be a summation of three things. Interface IP that connects the models together to give the designer some insight about where they're getting early before spending too much time and effort. And second, design platform that goes from early definition to fully finished chip with the ability to quickly turn around underneath one cockpit. And then finally, manufacturing. Manufacturing is extremely important. Manufacturing is the foundation of the cards we have, right? And various interconnects, various metal connections, various architectures, we have to work together to enable a robust and secure manufacturing of all chips together. Coming back to I guess the question I asked earlier, how can we make chip designers, how can we help them innovate? We talked about, we wanted to recognize the new design targets, the three targets we talked about earlier, right? We want to give them wings. We want to give them wings being interface IPs, end-to-end flow, and manufacturing enablement. I'm just going to say, we need to show them the road, right? When I first saw this invitation, I was super excited. Right, I was super excited because that is really exciting title, Road to Chiplets. In fact, I'm going to claim chiplets are the road to the next 1000X. Chiplets are the road to the 1000X. For the next decades, we should be envisioning and be prepared for a world where we're looking at a system optimization holistically across all dimensions, X, Y, and Z, not in discrete orders, all X, Y, and Z. We should be looking at integration of 100 plus chiplets heterogeneously, not homogeneously, 100 million interconnects horizontally and 10 billion vertical interconnects, a little bit beyond our capability today. And this is what I'm looking forward to for the next decade. So I look forward to travel on the road to the next 1000X via chiplets with all of you. Thank you.
Ming, thank you. That is an excellent talk and a very good vision. Let me ask you, what in your mind would limit realization of this vision?
Sky is the limit. Well, there are a lot of, that's a visionary answer, but I think there are a lot of challenges, right? But I really think, I want to just answer in two parts. I really think together, we should make it happen. You and I, everybody here should make it happen. This is what the world's need. Now, let me get back to today. Let me get back to reality, right? There's several challenges, right? I think chiplets are going to be severely impacted by the current stress on supply chain and geopolitical tension, more so than probably pure IP business, right? That's something we should be aware of. And the second thing is, I guess, this sliding scale, right? The tension pair of standardization versus proprietary IPs, right? I think that's a balance we need to achieve. I'd love to work with you together on that.
How about more pragmatic sort of technical issues like materials availability, power management, power delivery, interconnect characterization, test metrologies, or metrologies for process development? What's your view of all of those kind of limiters?
I think DFX and post-silicon validation, that kind of thing, will be quite challenging for 3D IC, right? It's a heterogeneous integration system where just intrinsically there'll be more corners, there'll be more unmodeled parts. Again, that is going to be challenging, right? And some of the challenges are technical, right? For example, if you have chiplet 1 sitting next to a chiplet 2 on a common base die, and whatever happens in chiplet 1 in terms of workload would probably propagate sideways to the chiplet 2. So the workload is no longer constrained, which means the thermal analysis would be a little bit interfering with each other. That's definitely a challenge, right? And some of the models may not be available, right? Depending on where you're getting the chiplets or dice from. That kind of goes back to, again, the standardization component to it. I think the DFX post-silicon portion of it would be, it has always been hard for advanced node, but I would say it'll be even harder.
Perfect. We have a couple of minutes for additional questions from the audience. If anybody else wants to type in a question in the Q&A session. I will continue asking Ming just because this has been a very visionary talk. In your mind, is there a succinct roadmap out there that tells us how we progress to make this vision happen, or is there a need for a succinct roadmap?
Um, we have a very distinguished panels here and certainly a very knowledgeable audience here. I don't know if I know everything. I don't know. So I would definitely caveat that first. I really love the way you frame the question as succinct roadmap because I think we have a lot of roadmaps. I think simplicity is what I have not accomplished yet. I think we need to have a simpler roadmap as opposed to it's a menu, right? The way I like to see it is let's give people the menu of manufacturing options, interface IPs, and a bunch of tools, right? The innovators, the chip designers, let's make them work it. I have not seen it, but it doesn't mean it exists. It does not exist. So I would
Perfect.
need some guidance on that succinct roadmap.
Perfect. Thank you very much, Ming. This was a very, very interesting talk. I
So once again, thank our sponsors, Advantest, Omcor, and Synopsys, who made this event possible. Um, Advantest rated the best ATE company 2021 in the VLSI Customer Satisfaction Survey of 2021. Omcor, as we heard an excellent overview from Dave as to their work, but as the leading OSAT with differentiators in the area of technology, quality, and service. Synopsys with their vision for supplying solutions from silicon to software. And with that, I will thank everybody for joining us today. And once again, thank you for your attention and your participation. And we look forward to seeing you again tomorrow at 8 a.m. Pacific. Thank you.